What is hockey? Ice hockey, otherwise known as hockey, is the ancestor of many different sports including field hockey, ball hockey, and floorball. In the game of hockey, two teams of 16 to 17, usually made up of 9 forwards, 6 defense, and 2 goalies, play against each other and attempt to score on the opposition's net using a 6-ounce black puck. The physics of hockey is a broad subject of analysis, which is why this video will clearly explain specific aspects of the game in the format of interplanetary play. The subjects covered will include kinematics, momentum and energy, fields, and kinetics. Kinematics is a branch of mechanics that is described through the motion of objects using words, diagrams, numbers, graphs, and equations. The goal of any study of kinematics is to develop sophisticated mental models that serve to describe and ultimately explain the motion of real-world objects. The variables that make up a kinematic equation consist of the following: distance, time taken for the object, acceleration of the object, and initial and final velocity of the object. Each of these variables impact the projectile of the hockey puck after release. Although these equations may accurately depict the kinematic projectile of a puck, in the format of interplanetary play, the puck's 4 main variables that impact the projectile will have changed. On Miranda, the ability for a puck to remain on its surface is highly unachievable due to the 0.07 meter per second squared force of gravity. Therefore, the projectile will have an added vertical distance. With this added vertical distance, the ability to calculate velocity of the object using the range equation will not be useful. The range equation can only be used when the release of the object is on the ground. Due to the addition of a vertical distance, the object's upward and downward velocity will not be the same. Not to mention, if the gravity of Miranda was greater than the Earth's, the ability for the puck to even lift off the surface would not be obtainable. Therefore, there will not be an existing projectile, and the capability of roofing would not be possible. Adding to this thought, if the force of gravity was much greater, a player on Miranda wouldn't be able to skate with a high velocity due to the fact that they cannot lift their feet off the ice in order to move forward. This will be talked about to a further extent in the kinetics section. In space, but more specifically on Miranda, the ability to determine what the speed of an object is cannot be done unless it is compared to another object in motion. This is where a frame of reference is useful. A frame of reference is a coordinate system for recording locations in time and was the backbone of Albert Einstein's theory of time dilation. In this theory, Einstein had the thought that if you were to synchronize a set of clocks, pick a point in between the clocks, and send a flash of light from that point in both directions, the clocks would read the same if they were synchronized. This theory was developed as a way to explain that time passes differently for different observers depending on the observer's motion. With this idea, Albert Einstein said that the faster the relative velocity, the greater the magnitude of time dilation. Relative velocity is the vector difference between the velocities of two bodies, that is, the velocity of a body with respect to another regarded as being at rest. For instance, in the interplanetary play of hockey, if a rocket ship was to pass by the puck, they would experience time dilation. That is, when the rocket passes the puck, the clock in the rocket ship visible from the puck's point of view would appear to be moving slower than the clock of the puck. Time dilation has been confirmed by several experiments and is the general idea that an object moving at higher speeds is seen as moving slower based on the reference frame of the observer. With this postulate in mind, if the force of gravity on Miranda was enough to keep the puck on the ice, i.e. much greater than the Earth's gravity, as a shot is taken from player A, the velocity based on their reference point would appear to be moving faster because the object is accelerating from its initial velocity of 0. Whereas the goalie, for instance, would see the puck's velocity as slower because it is already accelerated to its maximum velocity. This general idea is evidence that the ability for time and other factors in space is fairly difficult to calculate for. Therefore, kinematic equations that require time to be used would not be calculated correctly because the values for time vary as the puck travels through space. Equations that don't require time are: Although the equation to calculate for velocity is distance over time, therefore time must be used in this circumstance as well. The only way to solve for these equations is to have a set time that is constant throughout the entire space continuum, which is not logical due to the fact that gravity varies for every planet and every significant vertical distance. As objects move further from planet Earth, time passes more quickly based off of the theory of gravitational time dilation. Gravitational time dilation is yet another theory that states the higher the altitude, the slower the time. For example, due to Miranda's gravity of 0.079 meters per second squared, if the goalie was floating in space and player A was attached to a short rope on the surface of Miranda, the goalie would see player A as skating with a slower velocity than the actual velocity of player A. All of these variables are essential in calculating the velocity of an individual taking a slap shot in space. Not only a slap shot, but the ability to calculate the velocity of a player skating would be impacted due to the unrecognizable time in space.
Gravitational field is a field of force surrounding a body of mass in that another body would experience an attractive force. If you were to take a trip across the solar system and land on multiple planets, it would be recognizable that you weigh different on every planet. This is because the gravitational fields in every planet is different. Gravitational field strength is measured in newtons per kilogram, which is equivalent to the measurements for acceleration. The equation to find the gravitational field strength of an object is G equals F over m, where G is the gravitational field strength, F is the gravitational force, and m is the mass of an object. The moon of Uranus, Miranda, has a gravitational field strength of 0.079 newtons per kilogram. The gravity of Uranus pulls on Miranda, which generates a tidal force. A tidal force is the effect of gravity. It happens only when the gravitational force by one object to another is not consistent across it. Miranda's orbit around Uranus was once oval-shaped, moving it closer and further from Uranus. Because of Miranda's low gravity, playing hockey on it would be extremely difficult. For instance, if you were to shoot a puck in the air to get it out of your zone and over the opponents, in hockey this is called flicking, by the time the puck lands, it could possibly be the end of the period, and result affecting the game. On the other hand, if Miranda were to have a high gravity, when you are flicking the puck, then the ability for the puck to launch off the ground would not be done because of the greater force acting downwards. This increase of gravity would make it extremely difficult for the puck to leave the ice surface at any moment in the game.
A planet's gravitational force is determined by its mass, as shown here. Force of gravity is directly proportional to mass. The more mass a planet has, the greater gravitational field strength it'll have. Gravity has a huge effect on momentum. If Alexander Ovechkin, who has a weight of 104 kilograms on Earth, was skating at 4 meters per second, he has a momentum of 412 kilogram meters per second. If Ovechkin was to be skating at 4 meters per second again, on a planet with excess gravity, we'll say twice as much, he would carry twice the amount of momentum, since P for momentum is directly proportional to mass, as shown in that equation. This would allow Alexander Ovechkin to check or impact someone much harder. Sounds awesome, right? Not really. Should Ovechkin hit another person stationary against the boards and cause a completely elastic collision, this doubled momentum could be detrimental for both players. If an individual with inadequate equipment to be hit with double the momentum as if they were on Earth in a completely elastic collision, which lasted half a second, a force of 1,662 newtons of force would be produced in that hit. This is extremely jarring for someone just traveling at 4 meters per second. However, hockey players on the low end are able to travel at 9 meters per second. That would raise the force from 1,662 newtons to 3,750 newtons. A quick sharp blow that's delivered with some 3,300 newtons of force has a 25% chance of cracking the average person's rib. This would make playing hockey on a planet with more gravity some risky business. The opposite is true for a planet with less mass, therefore less gravitational field strength. Assuming there is enough gravity that players could skate properly, the hits will not be as severe due to players' decreased momentum. However, players may be able to skate faster since they feel lighter on the planet with less gravity. This would also proportionally increase the momentum of the players, as shown in this equation right here, with velocity being directly proportional to momentum.
Kinetics is a branch of physics associated with the study of forces acting on an object. On Miranda, due to the minimal force of gravity, the ability for these forces to be applied onto the player while they're skating is highly unachievable. For example, when playing hockey on Earth, the force applied onto the skater consists of the normal force, i.e. the force opposing the direction of gravity, the force of gravity, and the force applied in the direction of movement, and the force of friction opposing the direction of the force applied. In general, with the gravity of Miranda, the player would be floating off the ice, thus disabling the ability to apply a force in the preferred direction. On the other hand, if there was an immense amount of gravity on Miranda, the player would be able to land on the moon, but since the gravity is so strong, they would not be able to move. This is because the force of gravity would be stronger than any other force trying to act upon it, resulting in the player staying stationary and making it difficult to play the game. Due to the 0.079 meter per second squared force of gravity on Miranda, the gravity isn't strong enough to keep the player on the ice. So their direction they applied force would be upwards because this is their net movement. This would ultimately make the game unplayable. Whereas if the force of Miranda was to increase to be greater than the force of gravity on the Earth, on the free body diagram, there would be an existing force of gravity acting downwards on the object, and due to this, there will be a normal force opposing the direction of the player from moving upwards. Although the applied force in the preferred direction of movement wouldn't be as strong because the force of gravity is too powerful that the ability to have a strong stride would not be obtainable because there's too much resistive force acting downwards on the player. This downward force will make it extremely difficult to have a strong stride because the player cannot lift their feet off the ice. To also mention, on the free body diagram, there will be a minimal force of friction, so this would impact the ability for the skater to move at a greater velocity when relating it to Newton's third law. Newton's third law states that for every action force, there is an equal and opposite reaction force. Adhering to this law, if there is a minimal force of friction, when the player makes contact with the ice surface, there will be a weak action force resulting in a small distance and a slow velocity traveled. This was our Interplanetary sport project on hockey, and I hope you enjoyed it.